When water is boiled, the heat energy transferred to the water molecules allows it to escape into the atmosphere as water vapor. Just like when water is boiled, water vapor is released. When metals are heated to a high temperature, electrons are emitted. This process is known as thermionic emission. The amount of heat energy required for thermionic emission varies from metal to metal. For instance, thoriated tungsten requires much less heat energy than plain tungsten for thermionic emission. If you just supply heat to the metal, it does not mean you will notice thermionic emission. There is a minimum threshold heat requirement for thermionic emission, which varies from metal to metal. Since thoriated tungsten requires less heat than plain tungsten, we say that thoriated tungsten has a lower work function than plain tungsten. Increasing the temperature increases the rate of thermionic emission. With more heat, more electrons are excited enough to be emitted from the surface. Thermionic emission increases with a larger surface area. With more surface area, there are obviously more electrons which will be emitted. When the key is connected to a positive terminal, a current is noticed in the ammeter. The filament gets heated, and due to the potential difference, the electrons jump from the hot filament to the other side, thus completing the circuit. This proves the property of thermionic emission in metals, as there is no other path for the electrons to shift from the left to the right side. When an electron moves in an electric field, it gets attracted to the positive terminal and follows a parabolic path towards it. A stronger field will increase the force of attraction, and the path to the positive terminal will be shorter. You can experiment by ticking and unticking the check boxes. When an electron moves in a magnetic field, it is found to deflect. The dots indicate that the field is coming out of the screen. So in other words, see the face of the north pole of the magnet. The cross indicates that the field is growing into the screen. So you see the face of the south pole of the magnet. The direction of deflection of the electron is determined by Fleming's left-hand rule, which is described in detail in the electricity chapter. Be careful when determining the direction of current in applying Fleming's left-hand rule. The electron moves from left to right, so the conventional current is from right to left. Make sure your middle finger points to the left. The heated cathode emits electrons. These electrons are further accelerated by the anode. Then there are deflecting systems that the electrons have to pass through. One is the vertical deflecting system, which can control the electrons vertically, and the other is the horizontal deflecting system, which can control the electrons horizontally. This way, you can control the beam of electrons onto the screen. In a CRT television, the principle used is that of a cathode ray tube. The scans across the television are done 25 times a second. Since this is such a fast reproduction of the scene, it creates the illusion of a moving picture. In an atom, the atomic number represents the number of protons, and the mass number represents the sum of protons and neutrons. The protons and neutrons are embedded in the nucleus, whereas the electrons revolve around the nucleus. In the case of sodium, you can see that it has 11 protons, so its atomic number is 11. It also has 12 neutrons in the nucleus along with the 11 protons, so its mass number is 23. In neutral atoms, the number of electrons revolving will equal the number of protons in the nucleus. Isotopes are variants of an element. Take the example of carbon. One form of carbon has 6 protons and 6 neutrons, making its atomic number 6 and mass number 12. Another form of carbon has 6 protons and 7 neutrons, making its atomic number 6 and mass number 13. Since their atomic numbers are the same, but their mass numbers vary, they are known as isotopes. Take the case of sodium and magnesium. They have the same mass number, but different atomic numbers. So, the number of protons that they contain are different, but the sum of the protons and neutrons are identical. Isobars have the same mass number, but different atomic numbers. Isotones have the same number of neutrons but a different number of protons. Hence, both sodium and magnesium contain 12 neutrons but different number of protons. Their atomic numbers and mass numbers vary. Radioactive decay takes place in three ways. One of them is when an alpha particle is released. In the nucleus, 2 protons and 2 neutrons combine as an alpha particle, and the alpha particle is emitted. This reduces the atomic number and the mass number of the atom. Since the configuration of an alpha particle, atomic number 2 and mass number 4, is similar to that of a helium nucleus, the alpha particle is commonly referred to as a helium nucleus. Another mechanism of radioactivity is through the release of a beta particle. One neutron in the nucleus splits into a proton and an electron, so the combination is still neutral like that of the parent neutron. The electron is emitted in the form of a beta particle. The extra proton in the nucleus adds to the original number of protons, while the number of neutrons decreases by 1. Emission of gamma rays is another mechanism of radioactive decay. Gamma rays are electromagnetic waves from the nucleus, which travel at the speed of light. There is no change in the number of protons and electrons after the emission of a gamma ray. In a chemical reaction, an electron is released from the outermost shell, so there is no change in the nucleus. The atomic number and the mass number remain the same. In a nuclear reaction, the number of electrons in the outer shell do not change. Instead, there is an emission from the nucleus. The atomic number and the mass number undergo a change in nuclear reactions. The alpha and beta particles deflect in a magnetic field. Use Fleming's rule to determine the direction of the deflection or force. Remember that the direction of the electron or beta particle is upwards, whereas direction of the conventional current is downwards. So make sure you use the direction of conventional current in applying Fleming's left-hand rule. Gamma particles are not deflected. The alpha and beta particles deflect in an electric field. The alpha particles deflect towards the negative plate, since they are positively charged and get attracted by the negative plate. Similarly, the beta particles deflect towards the positive plate, since they are negatively charged. The gamma rays are not deflected. Alpha radiation is the weakest. and is stopped by a sheet of paper. Beta radiation is stronger and can be stopped by about a 1 millimeter thick piece of lead. Gamma particles have the highest penetrating power and can pass through almost 30 centimeter thick piece of iron. Although alpha particles are heavy and slow, when they travel the same distance as beta and gamma particles, they ionize particles around them the most. Gamma rays are very fast and have the least ionizing potential.